Hello everyone, this is Rui PCB, your trusted PCB partner. Today, we'll be discussing hierarchical versus flat schematic design in KiCad, which one is right for you. Generally speaking, KiCad recommends using hierarchical design as it provides a clearer structure and makes design reuse easier. For simple systems, flat design is also easy to implement, but designing complex systems in a flat structure is not so straightforward. So, what is flat design? In the past, especially before the computer era, most schematics were created this way. Flat design can be a single page or multiple pages to accommodate your schematic. If there are multiple pages, each page may contain content related to the others. For multi-page designs, there must also be a way to establish connections between the pages. This kind of cross-reference is called a label in KICD, and in fact, it should be a global label. Local labels are only effective within a single page. Another important tool is a power symbol. Typical examples include symbols like GND and VCC. Power symbols are global in flat design, meaning they are valid across all schematics. By default, they represent a global net. So, what is hierarchical design? Hierarchical design is a completely different design approach. In a sense, it can be compared to object-oriented programming. The main idea behind it is to introduce layers of abstraction, which makes it easier for people to understand complex systems. A hierarchical sheet symbol doesn't just represent a single schematic page. It's more like an object that defines an interface. In KiCad, such interfaces are implemented through hierarchical pins and hierarchical labels. However, global labels, such as power symbols, somewhat reduce the effectiveness of this design method. Now, let's look at the diagram. Flat design is much simpler, so we don't have a diagram for it, it's just different pages. This is what a hierarchical design structure looks like. At the very top, what we see is the first page, which is the top level schematic. Below that, there can be sub-schematics, and those sub-schematics might also have their own subsystem top level schematics. In cases where the structure is particularly complex, these schematics together form a more intricate system, which then generates a subsystem top level schematic again, a module, a, a block, which is then further broken down into various sub-schematics in this way. Now let's take a look at a flat design schematic. This is a flat schematic, and it's actually a pseudo-structure design. That is, it appears to be structured, but in reality, it doesn't design interfaces for each page. Instead, it still uses a flat approach with global labels, because in its top-level schematic, it only draws two blocks to represent two pages, but there are no port connections between the pages. The port connections are still achieved using these global labels. Since this schematic only has two pages, it's relatively simple, meaning it's easy to remember. I know that this page outputs externally, like here. There are only four ports and connects to the second page. So this kind of setup is quite simple and easy to remember. That is, we can still remember which global labels each page should have, and how to use these global labels on the next page. But if you imagine a situation with dozens of pages, it becomes very difficult to remember which global labels are on each page, and which global labels in the entire schematic can be reused. So at this point, structural design is introduced. Of course, when the number of pages reaches a certain level, structured design becomes a necessity. So this is a truly structured schematic. Right now, where we are is at a top level label, the top level schematic. You can see it has a 12V power supply, and then outputs several power rails externally. Since the power supply's labels are inherently global, the power module doesn't need to set up as many input and output ports to connect with other modules like these other modules do. Look, this is a very complex one. Let's take a look at this large section in the middle. You simply just double click to enter. So this particular view corresponds to precisely what we commonly refer to as the subsystem top-level schematic within the comprehensive drawings. After entering from the top-level schematic, you'll notice that it's still this kind of structure. There aren't components yet, but rather many different modules. That's because the system is too complex. So it uses subsystem schematics. Let's go further in. Now, this is the actual sub-schematic, which involves specific components and interfaces. Then we can go back to the previous level and take a look at those with only one layer. For example, the circuit here is relatively simple. It only has one layer. It encapsulates these functions into a single module and then displays it at the top level. In this way, it's very simple and also very clear. The outputs of each module are clearly defined, how many output pins and their functions. The internal pins can use local nets to complete the global network, and all the labels can be seen in the top level schematic. This allows us to clearly know how many labels we need to reserve for external connections in each subschematic. Moreover, these already completed subschematics can also be reused. For example, if another design also requires this module, I don't need to redraw it. I can simply copy this module over and reuse it. This makes system reuse very convenient as well. Alright, that's all for today's content. If you enjoyed this video, please subscribe to my channel for more videos. Thank you, everyone.